On July 12, 2022, the James Webb Space Telescope released an image that shattered cosmology. A single galaxy, JWST Z13.0, sitting 13.4 billion light-years away, shining 300 million years after the Big Bang, appeared impossibly massive, impossibly bright, impossibly structured. Here's the paradox. Despite observing light that left this galaxy when the universe was barely 2% of its current age, light stretched by cosmic expansion into infrared wavelengths invisible to human eyes, JWST revealed a galaxy that, according to our best models, shouldn't exist yet. Galaxies that young should be small, dim, chaotic. This one looks organized, evolved, old. How is it possible for a galaxy to be ancient when the universe itself was still an infant? And how much longer can JWST keep rewriting cosmic history before its fuel runs out? The James Webb Space Telescope launched Christmas Day, 2021, carrying humanity's most ambitious question: what did the first galaxies look like? But here's the counterintuitive detail. JWST wasn't supposed to challenge our understanding of early galaxies. It was supposed to confirm it. The standard cosmological model predicted that the first galaxies, forming 100–300 million years after the Big Bang, would be small, messy clumps of stars. Low mass, dim, disorganized. Building blocks that would slowly merge over billions of years into the grand spirals and ellipticals we see today. JWST's mission: catch those first, primitive galaxies in infrared light. The special circumstance that enabled success. JWST's unprecedented infrared sensitivity combined with gravitational lensing. Some of the deepest images JWST captured weren't random patches of sky. They were aimed at massive galaxy clusters whose gravity bends and magnifies light from even more distant galaxies behind them. This natural cosmic telescope effect amplified faint distant galaxies by factors of 10⁻⁰x, making the invisible visible. 5 achievements that built toward the paradigm-breaking discovery. Achievement 1. JWST First Deep Field, July 11, 2022. The first released image showed galaxy cluster SMACS 0723 as it appeared 4.6 billion years ago. But in the background, magnified by the cluster's gravity, thousands of even more distant galaxies appeared, some from just 600 million years after the Big Bang. Achievement 2. Detection of Glass Z13, July 2022. Just weeks into operations, JWST spotted a galaxy candidate at redshift Z13, meaning its light was stretched by a factor of 14 due to cosmic expansion. If confirmed, it formed just 300 million years post-Big Bang. Achievement 3. Spectroscopic confirmation, October 2022. JWST's NIR spec didn't just image distant galaxies, it took their spectra, measuring exact redshifts via hydrogen emission lines. JWST Z13.0 was confirmed at Z.13.2, placing it 13.4 billion light-years away in distance, 13.5 billion years ago in time. Achievement 4. Unexpected galaxy maturity. The paradigm breaker: these ultra-distant galaxies weren't dim, chaotic proto-galaxies. They were bright, some rivaling the luminosity of the Milky Way, and showed signs of structure: spiral arms, central bulges, even dust lanes. Achievement 5. The impossible galaxy population. By mid-2023, JWST had found dozens of galaxy candidates at Z10. Statistical analysis showed there were 10⁻⁰x more bright, massive galaxies at these early epochs than models predicted. The universe's first galaxies weren't supposed to grow up this fast. 2 telescopes, 2 decades, 2 completely different early universes. Hubble's view, Hubble Space Telescope, launched 1990, pushed to its absolute limits with the ultra-deep field. A 13-day exposure of a tiny patch of sky. It detected galaxies out to redshift Z11, roughly 400 million years post-Big Bang. These galaxies appeared as expected. Faint, small, irregular blobs. Hubble confirmed the standard model. Early galaxies were dim building blocks, slowly assembling into larger structures. Hubble's deepest images represented the heroic effort of an aging telescope working at the edge of its capabilities. But it was fundamentally limited. Its mirror was too small, 2.4 meters versus JWST's 6.5 meters, and its instruments couldn't see deep into infrared, where the most distant, red-shifted galaxies shine. JWST's view: JWST observed the same regions Hubble studied, but with 6.25x, the light-collecting area and infrared sensitivity, Hubble couldn't match. What JWST revealed, the faint blobs Hubble barely detected, exploded into rich detail. Galaxies Hubble missed entirely appeared by the hundreds. And most shocking, the Z10 galaxies weren't the expected faint proto-galaxies. They were luminous, structured, massive. Current status comparison. Hubble, 34 years operational. Instruments degrading, gyroscopes failing. Expected to deorbit 2030-2040. Its final deep fields represent the limit of visible light cosmology from space. JWST, 3+ years operational, full instrument suite functional, redefined the early universe in its first 6 months of science operations. Here's the relativity trick. The difference between Hubble's deepest view and JWST's may not seem like much. Both see galaxies from the universe's first billion years. But imagine you're trying to study early human civilization. Hubble's view is like seeing blurry aerial photos of ancient settlements. You know something's there, but details are lost. JWST's view is like walking through Pompeii with perfect lighting. Suddenly you see roads, buildings, art, structure you never knew existed. The difference isn't incremental, it's categorical. What Hubble achieved proved the early universe was there and broadly matched expectations. What JWST achieved revealed the early universe doesn't match expectations. Galaxies formed faster, grew brighter, and organized sooner than our models allow. Two commonly confused terms: look-back time versus light travel distance. Think of look-back time as when. It's how long ago the light we're seeing was emitted. JWST light left 13.5 billion years ago, just 300 million years after the Big Bang, which happened 13.8 billion years ago. That's the look-back time. Think of light travel distance as how far the photon traveled. 13.5 billion light-years, right? Wrong. Because space itself has been expanding while that photon was in flight, the galaxy isn't where it was when it emitted the light. It's much farther now. The actual current distance to JWST Z13 is roughly 33 billion light-years, more than twice the light travel distance. This is why redshift Z matters. Redshift measures how much space has stretched since the light was emitted. A galaxy at Z1 has its light stretched by a factor of 2. Wavelength doubled. Z2 means stretched by factor of 3. Z13.2 means stretched by factor of 14.2. The exact moment of transition when this galaxy went from expected to paradigm-breaking came when spectroscopic confirmation locked in its redshift. Before JWST, the handful of Z10 galaxy candidates from Hubble sat right on the prediction line. Faint, as expected. JWST's Z10 galaxies sit 10-100x above that line. Too bright, too massive, formed too fast. Significance: if these galaxies are real, and spectroscopy says they are, then either star formation was far more efficient in the early universe than models predict, converting gas into stars 10x faster, or the first stars were far more massive, burning hotter, brighter, dying faster. seeding galaxies with heavy elements earlier, or dark matter halos assembled faster, providing gravitational wells for gas to collapse into, accelerating galaxy formation, or our cosmological model is incomplete. Something about the early universe's expansion, dark energy, or initial conditions is wrong. Multi-stage timeline. 380,000 years post-Big Bang, universe cools enough for atoms to form. Cosmic dark ages begin. No stars yet. Roughly 100–200 million years. First stars ignite. Predicted. Not yet directly observed by JWST. 300 million years, Z13. JWST Z13-0 already shining brightly with structure. This is the shock. 400–500 million years, multiple massive galaxies confirmed. Population boom, JWST revealed. 1 billion years, Z6. Galaxies expected to look mature, but they already looked mature at 300 million years. The timeline compressed. The universe grew up faster than we thought possible. Restate the core mystery. How does a telescope 1 million miles from Earth detect galaxies from 300 million years after the Big Bang? Objects so distant, their light has been traveling for 13.5 billion years, stretched by cosmic expansion into wavelengths no human eye can see? The answer: engineering precision that borders on magic. The transmitter analogy: think of JWST Z13-0 as an ancient beacon. When its light left, the wavelengths were ultraviolet, energetic photons from hot young stars. But as that light traveled through expanding space for 13.5 billion years, each wavelength stretched by a factor of 14. UV light became near-infrared. Visible light became mid-infrared. By the time it reaches us, the galaxy's signal is completely outside the range of optical telescopes like Hubble. JWST's instruments, NIRCam and NIRSpec, detect 0.6 to 5 micron infrared, exactly where Zeta-13 galaxies now shine. Household comparison: JWST's 6.5-meter gold-coated mirror is like a 21-foot satellite dish, but for light instead of radio. The 18 hexagonal segments align to 10 nanometer precision. If the mirror were scaled to the size of the United States, each segment would be positioned accurately to within 1.5 inches. Signal travel time perspective ladder. Layer 1. Light leaves JWST Z13-0, 300 million years after the Big Bang. The photons begin their journey across an expanding universe. Layer 2. 13.5 billion years pass. Dinosaurs rise and fall on Earth. Humans evolve. Civilizations build telescopes. All while these photons coast through intergalactic space, redshifting continuously. Layer 3. The photons reach JWST's mirror at L2, 1 million miles from Earth. JWST detects them, converts photons to digital signal, transmits to Earth. Data travel time, 5 seconds. We're seeing the universe as it was when it was 2% of its current age, using photons that are older than Earth itself. Signal degradation by inverse square law. JWST Z13-0 is at a co-moving distance of roughly 33 billion light-years. Even accounting for the galaxy's intrinsic luminosity, roughly 1 billion suns. By the time its light reaches us, it's dimmed by a factor of roughly 1040. Each square meter of JWST's mirror collects maybe a few photons per second from this galaxy. But here's the miracle: JWST's detectors, cooled to 7 Kelvin, 266 degrees, can count individual photons. Over a 10-hour exposure, those few photons per second add up to enough signal to not just detect the galaxy, but measure its spectrum, determine its redshift, analyze its stellar population. How massive the receiver must be. JWST's 25-square-meter mirror is near the practical limit for current space launch technology. Future concepts: LUVOIR with a 15-meter mirror, HABEX, would see even fainter more distant galaxies. Ground-based telescopes can't compete. Earth's atmosphere absorbs the exact infrared wavelengths where high redshift galaxies shine. You must go to space. Global network ensuring 24/7 coverage. JWST transmits data to Earth via NASA's Deep Space Network, 70-meter dish antennas in California, Spain, and Australia, positioned to keep at least one in view of L2 at all times. Each observation of a field like JADE's is coordinated. Exposures planned months in advance, data downlinked over days, processed by teams worldwide, spectra analyzed by specialists in galaxy formation, cosmology, and data calibration. Finding galaxies like JD's GS-Z13-0 isn't a single eureka moment. It's thousands of hours of observation, petabytes of data, and hundreds of scientists cross-checking every detail. Because if you're going to claim you found a galaxy that breaks cosmology, you'd better be certain. Here's why the normal solution doesn't work. JWST can't be refueled or serviced. Hubble orbited 340 miles up, reachable by space shuttle. Astronauts visited 5 times, swapping instruments, fixing gyroscopes. JWST sits at L2, 1 million miles away, 4 times farther than the Moon. No spacecraft can reach it. Every system must last on what it launched with. The limiting factor: hydrazine propellant for station-keeping thrusters. JWST must fire thrusters every few weeks to maintain its precise L2 halo orbit and to counteract solar radiation pressure, the literal push of sunlight hitting its massive sunshield. Starting capacity in 2021, 240 liters hydrazine, budgeted for 10-year mission. Current capacity in 2025, roughly 210 liters remaining, 87.5% still available. Why better than expected? The Ariane 5 rocket's insertion burn was so accurate that JWST used far less fuel reaching L2 than worst-case estimates. Engineers now project 20-plus years of operation. Conservation measures. Reaction wheels handle most telescope pointing, saving thruster fuel for momentum management. Observation schedules optimized to minimize fuel-expensive slew maneuvers between targets. Passive thermal control via the 5-layer sun shield keeps instruments cold without active cooling, except MIRI's cryo-cooler. Emotional artifact with finality. There will come a day, perhaps in the early 2040s, when JWST's cameras capture their last deep field. The final photons from the universe's first galaxies will be recorded. The data will transmit home. Then, fuel exhausted, JWST will drift from L2 into an independent solar orbit. It will continue floating through space indefinitely, carrying the etched names of 10,000 engineers, silently watching the cosmos but unable to tell us what it sees. Minimal current operations. As of 2025, JWST operates at full capacity. All instruments functional, full observation schedule, deep surveys ongoing. Projected declining trajectory: 2025-2035, full operations, completion of major deep surveys, JADES, SEERS, Cosmos Webb, potential discovery of Z15 galaxies closer to the true first light, 2035-2043, fuel-limited operations, fewer targets per year, prioritization of highest science value observations, 2043+, propellant depletion. Mission ends. JWST goes silent. Every deep field image, every galaxy spectrum, every paradigm-breaking discovery exists within this finite window. Problem 1. Micrometeoroid strikes. May 2022, present. Between May 2022 and early 2025, JWST's primary mirror was hit by 6 micrometeoroids, tiny debris fragments traveling roughly 20,000 light-years. Why critical? Each impact creates a permanent crater in the gold-coated beryllium mirror. Segment C3's 5-micron crater distorts the wavefront, reducing the telescope's ability to focus light sharply, critical for detecting faint, distant galaxies like JADE's GS-Z13-0. Automated solution. JWST's wavefront sensing system detects aberrations within hours. Onboard computers command the affected segment's actuators to adjust position and curvature by nanometers, compensating for the damage. Resolution. Overall image quality remains at 99% of pre-impact performance, despite 6 strikes. Ongoing threat. Impacts occur every roughly 2 months, 4x faster than pre-launch models predicted. Each adds permanent, irreparable damage. By the 2030s, cumulative degradation may limit JWST's ability to see the faintest high redshift galaxies. Deep field implication. Finding Z15 galaxies, even farther than JD's GS-Z13-0, requires perfect optical performance. Every micrometeoroid strike narrows the window for these discoveries. Problem 2. MIRI Grating Wheel Friction Anomaly, August 2022. JWST's mid-infrared instrument began showing increased mechanical resistance in its internal grating wheel, used to select wavelengths for spectroscopy. Why critical? MIRI covers 528 microns, wavelengths where the most distant galaxies, Z15, would appear. Losing MIRI means losing access to the most redshifted objects in the universe. Diagnosis? 3 months of remote testing across the 5-second Earth L2 communication delay. Engineers discovered that at MIRI's operating temperature, 260 graus, lubricants behave unpredictably. Certain wheel positions, 15 to 25 degrees rotation, experienced excessive friction. Manual fix. New operational procedures avoid the problematic rotation range. MIRI spectroscopy now uses longer exposures with the wheel held in safe positions rather than continuous scanning. Resolution. As of 2025, MIRI operates in all modes with adapted procedures. Friction levels stable. No further degradation observed. Deep field implication. MIRI's continued health is essential for confirming ultra-high redshift galaxies beyond Z13. Its unique wavelength coverage can't be replicated by any other instrument. Future problem 3. Detector radiation damage, anticipated 2030s. JWST's HGCDT infrared detectors gradually accumulate damage from cosmic ray impacts, high-energy particles that cause permanent hot pixels and sensitivity loss. Proactive monitoring, software tracks damaged pixels and uses adjacent pixels for measurements. Calibration routines adjust for declining sensitivity. Anticipated solution. None. Hardware cannot be repaired. Software compensation works up to roughly 15-20 years of accumulated damage. Expected extension. If radiation damage progresses slower than models predict, JWST could conduct deep field surveys into the early 2040s. Deep field implication. As detector sensitivity declines, the faintest Z13 galaxies will disappear from view first. JWST's ability to push beyond JADE's GS-Z13-0 to even earlier cosmic epochs is time-limited. Ongoing challenges compound as JWST ages. Micrometeoroid damage accumulating on mirror segments, MIRI grating wheel showing signs of mechanical wear, infrared detectors slowly degrading from cosmic ray hits, propellant depleting with every station-keeping burn. JWST mission planners project fuel exhaustion, 2043, 22 years after launch. Time remaining from 2025, 18 years at most. That assumes no catastrophic sunshield puncture from large debris. No instrument failures beyond current workarounds. No unexpected propellant leaks. No premature failure of critical electronics. Every deep field exposure, every search for galaxies beyond Z13 exists within this contracting window. The universe's first galaxies formed over hundreds of millions of years. JWST will watch them for perhaps 2 decades before going silent. Somewhere out there, galaxies at Z-15, Z-20, maybe Z-30 are waiting to be found. Galaxies from just 100 million years after the Big Bang, the true first light. But if JWST doesn't find them in the next 10 to 15 years, while its instruments remain sharp, those galaxies may stay hidden until a next-generation telescope launches in the 2040s or 2050s. The clock ticks not just for JWST, but for answering the deepest question. How did the universe's first galaxies really form? Because right now, we know they formed faster than we thought possible. But we don't know how. And our window to find out is closing. JWST launched December 25, 2021. Designed for 10 years, may operate for 22. Compare its specs to modern consumer technology. Storage, 68 GB, less than a smartphone. Processing, 25 milliamperes, slower than a 1990s computer. Bandwidth, 28 Mbps downlink, slower than home internet. Mirror precision, 10 nanometer alignment, 30,000x better than LASIK surgery. Ancient computing, unmatched vision. JWST didn't just photograph distant galaxies. It shattered 13 billion years of certainty about how the universe evolved. The image of JWST Z332 is more than a pretty picture. It's proof that our story of cosmic history is incomplete. Galaxies grew up faster. Stars formed more efficiently. Structure emerged sooner than the equations allowed. We thought we understood galaxy formation. JWST showed us we were watching the wrong chapter. Until fuel runs out in the 2040s, JWST will keep probing deeper, searching for Z-15, Z-22, maybe even glimpsing the universe's true first light at Z-30. Each image rewrites textbooks. Each spectrum challenges models. Each deep field humbles us. The universe, it turns out, refuses to follow our expectations. And JWST, built with decades-old tech, flying on borrowed time, is the telescope forcing us to admit it. 13.5 billion years ago, a galaxy shone. In 2022, we finally saw it, and everything changed.